And welcome to the Winds and Currents webinar. Today, we're fortunate to have Patrice Klein, who's going to talk about the impact of ocean eddies and submesoscales on the atmospheric water cycle. So I'll let you take it away, Patrice.
Thank you very much, Sarah. So actually, this talk concerns some study undertaken by many people, including this list here with actor Udi Strobach, who is in Israel, Dimitris Menemelis and Andrea Molod, and Jimbo, Andy, and as well as Alex and Ernesto. And actually today I'm going to present the results from a first study that was led by Udi Strobach. And as I said before to Sarah, Hector and I, we talked with Tony Lee last week to figure out how to adjust this talk to Odyssey. So we will see if it works. So the motivation of this study about the impact of ocean mesoscale eddies and submesoscale on the atmospheric water cycle is that mesoscale eddies in the ocean with a size between 50 and 400 kilometers are mostly energetic at the mid-latitudes in the western boundary current and the ACC that are just the location of the atmospheric storm tracks. And we know that these eddies are associated with a significant mesoscale SST anomalies, which was confirmed by a recent study by Small and et al., and who analyzed the SST anomalies, that is the upper figure, and the latent heat fluxes anomalies, the bottom figure in the global ocean. So from the upper figure, we can see that SST anomalies are mostly energetic in the Kyushu extension, the Gulf Stream, and the ACC. And in addition, using two numerical simulation with a different resolution, Small et al. Found that, mesoscale eddies explain more than 50% of the SST anomalies. In addition, they found a strong correlation between the latent heat fluxes and the SST anomalies. And again, they found that the mesoscale eddies explain more than 50% of the latent heat fluxes in the global ocean. So the consequence is that the ocean mesoscale eddies moisten the atmosphere. And the correlation between mesoscale eddies and the latent heat fluxes can be illustrated by this figure here that shows the latent heat fluxes in the global ocean. This is a figure from our new coupled simulation. So on this figure, there are some larger scale patterns of latent heat fluxes that are mostly associated with the atmospheric weather. But there are also some small scale patterns, like for example, in the east of South Africa, like here. And if we zoom in this area, we get this picture here, where we can see the strong imprint of the mesoscale eddies on the latent heat fluxes. And we can see also there are some strong gradients of the latent heat fluxes at the edges of the mesoscale eddies here. So I would like just to summarize what has been found in the past 5 to 6 years. Most of the study show that the presence of mesoscale eddies not only increases the water vapor in the first 3,000 to 4,000 meters above the surface, but also the RC mechanism above eddies, including the strong gradients of surface heat fluxes I mentioned before, as well as the wind stress divergence and convergence related to the submesoscale fronts at the edges of the eddies, also energize the atmospheric storms. So all these results, I'm not going to to detail all these results, but they can be found in these papers here, and in particular in the last review by CO et al. whose co-authors include several members of the Odyssey science team. So, oops. So the question is, what are the consequences of these results associated with mesoscale eddies and submesoscale fronts on the atmospheric water cycle? Actually, these consequences can be illustrated by these three figures here that come from a recent paper by Tsu Liu that was published last year. The first figure on the left shows what we call the integrated water vapor transport, IVT. That is a proxy of the atmospheric rivers, AR. In short, if we focus on the Pacific Ocean here, the mesoscale eddies in the Kuroshio extension are going to moisten the atmosphere, as we said before, but they are going also to energize the atmospheric storms. In turn, these atmospheric storms, when they propagate eastward, are going to transport the water vapor toward the west coast of the US. And associated with this integrated water vapor transport, there are some precipitation, that is a middle figure, that can reach the west coast of the US. And if we zoom in this black box here, that is the right figure. Actually, what happens is that because of the mountains on the west coast of the US, the moist air masses are going to be pushed up to the tropopause, and which will trigger some precipitations. And actually, in their study, Tsu Liu found that the impact of the mesoscale through these processes, the impact of the mesoscale eddies in the Kuroshio can explain more than 30% of the heavy precipitation over the west coast of the US. And similar results were found by Ping Shang in his paper in 2022 for the Atlantic Ocean and for the ACC as well. So this is how the mesoscale eddies can impact the atmospheric water cycle. Now, these results question the mechanism associated with the surface heat fluxes over mesoscale eddies. And this mechanism can be illustrated by this very popular schematic from Flenger and collaborators. But I would like to mention that this mechanism has been examined for a long time by a lot of papers, starting with a paper by Dudley Shelton in 2004. So just to summarize this mechanism, if we consider a warm eddy, that is the left side, so we are here in the southern hemisphere. So this is why we have this cyclonic circulation here. So if we focus on the warm eddy, because of the large SST anomalies of our warm eddies, the air is unstable. And because of this instability, there is a mixing between the upper level and the surface, which means that since the wind speed is large at the upper level, the wind speed at the surface, because of this mixing, is going to increase. So we will have a wind anomalies, a positive wind anomalies, that is going to increase the latent heat fluxes. And associated with this increase of wind anomalies, there are some wind divergence and convergence at the edges of the eddies, those here. That is and of course the latent an increase of the latent heat flux gradient that are going to energize the atmospheric storms. So this is what happens above the warm eddies from all these studies. Now the opposite, of course, is true above cold eddies. But if we consider fully turbulent eddy field, the net effect of these eddies is to moisten the atmosphere and to energize the atmospheric storms, as found by this recent paper here. So, so actually, with Udi, we started to revisit this mechanism. And for that, we used this new couple ocean simulation that was developed in the context of the international project Diamond. So this couple model involves the MIT GCM for the ocean and the GEOS model for the atmosphere. And it was set up by Dimitris Medemelis and Andrea Molon and their teams. So the first simulation has a resolution of 1/16th of a degree in the atmosphere and 1/24th of a degree in the ocean. And it was integrated for about 14 months. So here are some pictures from this simulation. So the left figure shows total precipitable water vapor, and the right figure shows the classical ocean current in the ocean. So you can see that there is a big difference between the scales, the atmospheric scales and the ocean scales. But I should say that the output of this simulation are available to everyone in the community. And if you want to have some ideas about the potential of this simulation, you can watch a lot of movies that are found on this website here. At last, I should add that there is a new simulation that is in progress. That is integrated by, again, Dimitris and Andrea with a resolution double. So in this first study with Rudy, we focus mostly on the Gulf Stream area. And this figure here shows on the left the latent heat fluxes in the Gulf Stream and the SST field in the Gulf Stream. So on these figures, the black contours corresponds to the SST isoline, and the green arrows correspond to the wind speed. So for example, if we look at what happens here, we can see that there is an intensification of the wind speed over warm eddies, and where the latent heat fluxes are quite strong. And also, if we look at the SST field, we can see that there are some strong SST gradients that can reach a magnitude of about 4 degrees per 10 kilometers. And the same occur, of course, for the latent heat fluxes. Here we can have gradients of the latent heat fluxes with a magnitude of about 200 to 300 watts per meter square per 10 kilometers. So this field actually emphasizes the importance of the submesoscale SST fronts. And because of that, in this study, we focused on the submesoscales, and we computed wind stress divergence and convergence in this simulation. So these wind stress convergence and divergence are shown on the right figures here, and in color. And again, the green arrows correspond to the wind field. And so the wind is a southward wind in this case here. So if we zoom in this area, that is the bottom figure, the bottom right figure here, we can see that there is a strong intensification of the wind stress convergence and divergence just at the location of the SST fronts here. And this explains that this wind stress convergence and divergence explain that the wind anomalies above warm eddies, for example, can have a magnitude of about 4 to 5 meters per second, when the mean wind speed is about 12 to 15 meters per second, which is quite huge actually. And also, these wind stress divergence and convergence are associated with intense vertical velocity in the atmosphere that can reach a magnitude of about 1 meter per second at an altitude of 3,000 meters. And some of the vertical velocity can reach the tropopause level. And actually, if we compare what we get about the magnitude of the wind stress divergence, convergence, and vertical velocity field with what was published in the recent papers. It turns out that because of the resolution of the simulation, the vertical velocity is about 1 order of magnitude larger than what was found in the recent studies. So what we did with Woody after that, we tried to figure out what happens in the atmosphere. And for that, we plot some vertical sections in the atmosphere. And this is what we have here. So on this figure, the top figures are again the SST field and the latent heat flux field in the Gulf Stream area. So we plotted the vertical section along, if we look at the SST field, along this green line, this meridional green line here. This meridional green line is to cross a strong SST front here. The vertical section is the figure just below here. And, actually it goes up to an altitude of about 3,000 meters. On this figure in color shows the wind anomaly. So you have to know that the mean wind field is southward, so it is negative. And here, so it means the wind is blowing from from the north to the south here, which means that when the wind anomaly is positive, that corresponds to a deceleration of the wind field. And when the color is blue, it corresponds to an acceleration of the wind field. So this is what we have here. Now the dotted line shows the height of the atmospheric planetary boundary layer. The black bar here corresponds to the location of the SST, the strong SST front here. So what we have found with Woody is that there is a secondary circulation that is much better emphasized here. And a secondary circulation that is going to bring some air from upper level down to the surface above the warm eddies here, where the wind anomalies are going to be stronger here. And the wind anomalies in this case is not quite large. It's about between 1.5 and 2 meters per second. The mean wind field is not large as well. So this is how the wind divergence and convergence triggered by submesoscale SST fronts can impact the mesoscale latent heat fluxes. And again, here we have not the mixing between the upper level and the surface. We have just a secondary circulation that is going to bring some dry and air from the upper level down to the surface here. And so in all what we have done is it turns out that the wind stress divergence and convergence is a good index to explain the latent heat flux increase due to a turbulent eddy field, and also it is a good index to explain how such a field can energize the atmospheric storms. So to better understand the impact of the wind stress divergence and convergence, what we have done is we have estimated the relationship between the wind stress divergence and the gradient of the SST. So this relationship has been studied for a long time, starting with what the Shelton did in 2004. And just to show the similitude and the differences between what Dudley found using QuizCat data and what we have found with the high resolution simulation, I have plotted these two figures here. The left figure shows the relationship between the wind stress divergence and the SST gradients using QuizCat data and AMSER data. And so they found that the slope is about 1.65. So we did exactly the same calculation here using the numerical model. And we used exactly the same units as Shelton et al. Used in their paper. So what we have found, and this is here in the Kuroshio, but in the Gulf Stream, this is exactly the same. Actually, what we have found is that the slope is quite similar. Here it's about 1.6 or something like that, very similar. The main difference is the order of magnitude of the scale range on the x-axis for the SST gradients and the wind stress divergence and convergence. There is a difference of, by a factor 50, which means that this range of scales is 50 times larger than what you can get from the observation. And the same for the wind stress divergence. And now, if we want to compare what we get from this higher resolution simulation with what we can get from observation, I put this blue box here. So this blue box corresponds to what we can get from the observation. And this here is the red curve shows what we can get when the resolution is much higher. So I have three comments about this figure here, about these results. So first, as I said, there is no observations to validate the numerical results outside the blue box. The second comment is that usually the ocean currents can have an impact on the wind stress divergence or the wind stress curve. This is true for the wind stress curve, but this is not true for the wind stress divergence, because the ocean divergence, at least at the resolution we have now, is too weak to impact the wind stress divergence. And this is what we have found, but this is also what Lionel and collaborators have found in their last JGR paper. And the third comment I would like to make is that there is a strong correlation between the wind stress divergence and the SST gradients is only found for the strong winds. And I would like to emphasize that. So this is here we plotted the correlation between the wind stress divergence and the SST gradients as a function of the wind speed here. So what we can see is that when the wind, this correlation becomes significant only when the wind speed is larger than 10 meters per second. When the wind speed is smaller than 6 meters per second, the correlation is very weak and even can be negative here. And then there is this intermediate scale here. So the interpretation of that is that for the wind speed larger than 10 meters per second, so the wind stress divergence is mostly explained by the arguments I mentioned before about momentum mixing or the secondary circulation argument we found with UD. Now for the wind speed smaller than 6 meters per second, it turns out that the wind stress should be mostly explained by the Linson mechanism, which means that the wind stress divergence should be associated with the Laplacian of the SST and not with the gradient of the SST. And that was found by many papers, and in particular by Julien Lambert and collaborators. Now for the intermediate wind speed, as Alexis Poussard, Guillaume Lapère, and Riguel Plougonvin found, it seems that both mechanisms are involved. But now, in terms of the impact of ocean eddies and submesoscale on the atmospheric water cycle, we have seen that what is important is the atmospheric storms, since the atmospheric storms are going to transport the water vapor across the ocean. And these atmospheric storms are associated with a strong wind. So it appears that the strong conditions for this impact on the atmospheric water cycle are most important. And this is my last slide before the discussion. The question is the model right outside this blue box here, which means that we need high observation of a high resolution wind stress, high resolution SST, and higher resolution ocean currents, as we discussed with Tony last week. So I'm going to stop here. This is just a summary of what we have found. So I'm going to keep that on the screen. And if you have questions, we can discuss now.
Thank you, Patrice. That was wonderful. Big round of applause. And questions, discussion. Maybe I'll start with a critical question for Odyssey, that you've made a really strong case for high resolution SST. That's not something that Odyssey has planned to measure, but it's something that is possible from other instruments. How important do you think it is that that's simultaneous?
I think well, this is again something we discussed with Tony last week, and I think that it is very good to raise this point here. We need higher resolution SST, and so far we have some infrared images that can give us high resolution SST. Unfortunately, these infrared images are mostly affected by clouds. And since we are looking at the, I mean, we want to consider the atmospheric storm, so it means that there will be a lot of clouds, and we cannot use infrared images. So we need to use some other images, like microwave images from AMSR, for example, but the resolution is not high enough. So this is why we need also ocean currents, because if we use both ocean currents and lower resolution SST images from AMSR, we can retrieve the higher resolution SST using some Lagrangian method, as for example, Stefano Berti and Guillaume Lapère did some years ago, as Rosemary Moreau and Guillaume Dancos did also for the salinity. So we should be able, if we have access to ocean currents with a higher resolution, we should be able to retrieve the SST field with a resolution that we need here. For example, about 4 degrees Celsius per kilometer, per 10 kilometers.
Thanks. Jérôme Dubourg has a question in the chat. I can just read it. Same question for Odyssey. What resolution is needed for wind and current observations?
Good question. Here, we have a simulation with a resolution of 1/16 of a degree in the atmosphere, 1/24 of a degree in the atmosphere in the ocean, which means that the resolution is 4 kilometers in the ocean and 6 kilometers in the atmosphere. So this is a resolution for the numerical simulation. Now, in terms of physical, in terms of the currents and the wind field and the wind stress we can get from this simulation, I should say we have to multiply this 4 kilometers and 6 kilometers by a factor of about 4. And which means that if we have access to ocean currents with a resolution of 10 kilometers or 15 kilometers, the same for the wind stress, we should be able to find out the wind stress, the relationship of the wind stress divergence and SST gradients, as we have found in this numerical simulation. So again, for Odyssey, I think this is something we should be able to do. And at the present time, Hector is doing an OC study using Odyssey to figure out whether we can retrieve the correct magnitude of the wind stress divergence and convergence. So this is a study in progress.
Thanks. Tom Farrar has his hand up.
Thanks for the nice talk, Patrice. That was really interesting. It seems like these results are mostly focused on the strong SST front at the Gulf Stream. So you mentioned submesoscale SST fronts, but a lot of those can be, relatively small absolute SST changes. And so I was wondering if this is a process that's generically operating throughout the world ocean, or if it's more focused on the boundary current regions.
This is a good question, actually. So we did the same, Hector did the same analysis in the Kuroshio extension. And the last figure I showed was from the Kuroshio extension. The gradients, the SST gradients are about the same, and they are associated with energetic mesoscale eddies. We have to do that in the ACC, and in the ACC, there is a student, Luna, who is a PhD student with Andy Thompson, and who is doing something similar, not for the wind stress divergence, but for the wind stress curve. And Luna and Andy should be able to answer to that question. Now, if we want to figure out if this is true, for example, in the California current system, I'm not so sure. To be frank, I'm not so sure because, as you said, the SST gradients are not so large. And the same for the eastern part of the ocean Atlantic, actually. So this should work at least for the western boundary current for the ACC. But again, this in terms of the atmospheric water cycle, and in terms of the heavy precipitation or the extreme events, these currents are very important. Now, for the other part of the world, we are not so sure. I think the magnitude should be much smaller, but this is something we have to investigate.
Thanks.
So maybe Andy Thompson has his hand up, and maybe that follows from what Patrice just said or not. Go ahead, Andy.
Yeah, no, I mean, I can just very quickly say that I think Tom's question is a good one. It does look at these strong correlations do show up in the Southern Ocean, but then again, that's an energetic region, but it's a much larger energetic region than just the western boundary currents. So if you're thinking about air-sea interactions, that's it's a fairly large region where that's important. Patrice, really nice talk. Thanks for sharing that with everyone. It looks like I have a question that's similar to Rick's that's in the chat. So maybe I'll ask it for both, but maybe he's got a slightly different question. You showed that the correlation coefficient between wind stress divergence and SST gradient was a function of wind speed. And I had a question as to whether you've tested whether that dependence on the wind speed is the same in, say, like the Gulf Stream and the Kuroshio, or the same in different seasons?
Oh, okay. This is the same, actually. So we analyzed that for 3 months. We didn't do analysis every season, actually. So this is something we have to do. Now, we did that in the Kuroshio, we did that in the Gulf Stream, and it turns out that the correlation is about the same. But that was for during the winter season, actually. So now, whether this happens during the summer, we are not so sure. Because I mean, during the summer, the atmospheric storms are much weaker, and but this is something we have to investigate. No, this is correct.
Okay, great. And yeah, thank you for Patrice. Thank you for mentioning that Luna was leading the work in the Southern Ocean. So if Luna wants to chime in with anything else, I think she's on the call. Yeah.
Okay, thanks, Andy.
Yep.
Thanks. Rick, did you want to add to that question?
No. I was just posting that I thank you both for asking it, Andy, and for answering it, Patrice. No, that is kind of related. I guess an elaboration is on. I mean, it's since the strong storm, strong wind issue is relevant here. The winter storms are really interesting for that reason alone. And we do have good evidence in the summertime that these impacts, these vertically stacked impacts on ECMWF analysis have occurred. But the slantwise impacts on wintertime storms are more difficult to capture and potentially have greater incremental impacts in perhaps even into the older work from Claude Franquignoul, on monthly time scales. Those were very difficult to unpack at these shorter time scales, and I don't think that really has been addressed entirely. The connection between the short time scale processes and these long time scale impacts on atmospheric teleconnections. Just a comment.
I totally agree. And actually, we can find, for example, we can compare what we have found about the correlation between the wind stress divergence and the SST field, and the gradient of the SST with what Milobe et al. Found in the Gulf Stream about, 14 years ago. And what they found out is that the wind convergence or divergence is mostly related to the Laplacian of the SST. And this is because they used a low resolution field. And if you have a low resolution wind field, you are not going to take into account the high frequency winds and whose magnitude in terms of wind speed is quite large. So you are going to miss that, And I think this is, my feeling is that this is why there is a discrepancy between what people have found about the large-scale circulation in the atmosphere and the ocean, like Claude Franquignoul found, and what we have here.
Yeah, thank you.
Thanks. Can we go back to Fabrice's question in the chat? Fabrice, do you want to just go ahead and ask it?
Well, just following up on the first question is on the fact that, yes, SST is very important for many things. And the question is, how much can we demonstrate benefits on getting higher resolution SST fields that can be used for this type of analysis? And what's the best place to do that compared to what we have to do with altimetry? So I don't know if anybody wants to answer that, but maybe that's something we need to tackle in the science team.
Again, if we want to focus on the atmospheric storm, because this is the most energetic events in the atmosphere and that are going to impact the integrated water vapor transport, and also this is when the mesoscale eddies are very important. We don't have a high resolution SST. And so we have to retrieve high resolution SST from what we have now, that is microwave SST, whose resolution is much lower than what we need. And but if we have access to ocean currents at high resolution, again, we can retrieve a good estimation of the high resolution SST. But Fabrice, why did you mention the altimeter? Okay.
Oops. Muted.
You are muted, Fabrice.
The question is today we already have altimetry and people do Lagrangian estimation of current fields from altimetry. And so, I know we get much better resolution with Doppler currents with Odyssey, but we haven't translated that into Lagrangian currents and looking at the impact of that on the SSF field. And I think maybe that would be a worthwhile effort. Mm-hmm. And the question is, so I see that you're pointing more to the mid-latitude storms, but what about the tropics and the impact there? What do you think that maybe that could be interesting too? or it's completely different processes?
Okay, yes. Well, for the first part of your question about altimetry, I think Rosemary Moreau and Guillaume Dancos did a nice study for the salinity, because they use some salinity from satellite observation, and using ocean currents from Aviso or something like that, they were able to retrieve the SSS gradients with a resolution much higher. So I think we can do something like that using the existing Aviso products, or even using an OC with a SWOT. But and just to figure out what ODC, what new information we can get from ODC in terms of the SST gradient. I think this is a good question. Now, for the tropics, I cannot answer your question, because we have to figure out what happens, whether we have not a lot of mesoscale eddies in the tropics. We have just the tropical instabilities. And to be frank, I don't know what we can find when we study that. We have still to do that.
Okay, thank you. Nice talk.
And thank you, Patrice.
So Larry O'Neill had his hand up for a long time. Larry, did you want to go ahead and ask?
Yeah, sure. I was going to go in a second, but I just had a question. So there's been about at least over the Gulf Stream, is that the last 5 or 10 years, there's been a lot of work to show how storms really kind of confound, looking at these relationships between the wind and the SST, in particular the vertical wind velocities in the SST, and how storms, just a few very strong storms, affect those. And I was wondering if you've thought about that in your analysis.
About the impact, you mean the vertical velocity on the atmospheric storms?
Yeah, because there have been a couple of papers that have shown that, like the vertical velocity section you've shown, those upward time mean patterns are mostly just storms that tend to propagate along the Gulf Stream.
No, absolutely. No, this is a very, very nice question, actually, because I say that because we started to analyze what happens about how the vertical velocity field can impact the atmospheric storms. For atmospheric storms, we talk about the synoptic system. But what happens in this simulation, and what we have found, and you can see that on the movies, actually, what happens is that the synoptic atmospheric storms have a scale of about 1,000 kilometers or 2,000 kilometers, which is quite large. But you have these atmospheric fronts, and these atmospheric fronts can be impacted by the mesoscale eddies and by submesoscale SST fronts. This is that was shown by papers by Parfit and collaborators, Rata et al., etc. But in addition to that, what we have found, and we don't understand well, is that in the lower level of the troposphere, that is in the first 3,000 or 4,000 meters above the surface, we have some small scale storm, what we call in the atmosphere mesoscale storms, and that propagate along the gradients of SST. And we have that quite often, in particular during the winter time. And the question is whether these mesoscale storms are correct or not. I mean, if there are some physical explanation for these mesoscale atmospheric storms. And the second question is how do they interact with the synoptic atmospheric storms? So we don't know. We have just observed that. And I think that would be very interesting to investigate more about what happens on that.
Fabrice? Yeah, Hervé speaking. So just a remark about this point. SST gradient can induce PV anomalies in the atmospheric boundary layer, which are coupled which can interact with PV anomaly at high levels. When this coupling occurs, the synoptic perturbation, the cyclonic perturbation can be explosive. So this point out the importance of the SST gradient and the latent heat flux anomaly induced by the SST gradient, because they induce PV anomalies in the mood layer, which can interact with high levels.
I think this is a very good comment, Hervé. This is a very
we
good
saw
comment.
that during the FASTEX experiment in 1997.
Yes, a long time ago. Yeah.
Yes.
Yes, no, I see a very good comment. I think we should do this analysis to figure out what happens, because actually all these vertical velocity fields we have found out, can reach an altitude much above the height of the atmospheric planetary boundary layer. So there is a connection between the free troposphere and the surface.
Yes, absolutely.
Yeah. So again, we have to investigate that. And again, this couple simulation is beautiful for that, because we have the resolution. This simulation has been integrated for 1 year, more than 1 year, and it covers all the ocean in the world. So you can do some analysis in the Kuroshio, in the Gulf Stream, and other parts of the world. I'm sure that what you are saying maybe can be true in some areas and not true in some other areas.
Hervé, you had a question in the chat. Did you cover that, or do you want to expand and ask that question as well?
I was wondering if is the secondary circulation, is it an adjustrophic circulation or an anomaly from the average wind in the plot you presented?
Or is this just an anomaly with respect to the mean wind?
With the mean wind, okay.
Yes. No, this is not the classical secondary circulation as you can get from a geostrophic front, for example.
Yes.
Tony.
Thanks. It's really informative talk, and has a lot of arguments that we can use for the Odyssey missions. So I have a question and a comment. My first question is related to the seasonal variation of the coupling. So if you go back to the plot, the linear plot of the SST gradient and wind stress divergence, comparing with the Chilton study. This one. So it'd be great to look at whether the seasonal variation of the coupling is just moving along this straight line here, meaning that in different seasons you have different dynamic range of the SST gradient versus wind stress divergence, or whether the slopes are actually different. So distinguishing the dynamic range in this plot as in the context seasonal variation versus the whole slope is different.
Oh, okay.
Different seasons. So that's one.
This is a good question, Tony, and actually we can do that quite quickly.
Yeah, thank you. And my comment, okay, thank you. My comment is also related to the importance of currents in this whole coupling processes. So much of the material they discussed highlighted the importance of the SST gradient to wind stress or SST Laplacian in the lower wind speed range, as you mentioned. So ocean currents' importance is in the context of deriving final SST gradient. So that's one of the arguments that you use. But as we discussed and also pointed out by someone, probably Gerald or Rick, in a chat, that the similar mission, the Copernicus imaging microwave radiometer, I think scheduled for launch by 2027, will provide 15-kilometer microwave SST. And so that's quite a bit finer than the current 55-kilometer from MEMSER. And then the question is, if the importance of ocean current is limited in terms of deriving SST gradient, given the upcoming mission, how important is ocean currents in this whole story of submesoscale coupling and impact on the atmosphere, including the storm? My understanding is that the submesoscale coupling is more than just SST gradient. There are currents associated with it, but I don't know how to demonstrate that, given that the discussion is more on the SST and wind coupling and the impact on heat flux, as opposed to be on the dynamic coupling between wind and currents. So I don't know if one can make some diagnostic or related to plot like this to say that currents are important too, an important part of the story too. Then it will be a essential argument for the Odyssey mission. Sorry for my long comment.
No, it's okay. No, I think this is a very good comment, Tony. And actually, with Hector, we have started to figure out whether we can correlate the wind stress divergence, not with ocean current divergence, because as I said, ocean current divergence are quite weak, but with a relative vorticity. So the argument behind that is that these SST fronts are usually some ocean fronts, which means that if when the SST is an important component of the buoyancy field, and when you have an ocean front like an atmospheric front, you have some relative vorticity associated with these fronts that can be quite high. So we started to figure out whether we can get the same plots as the one that is on the screen here, with a relative vorticity field. So that was just a test, because we know that SST fronts are related to the relative vorticity or to the strain field. And so far we have not found a good relationship, but there is still some work to do on that. I think from the plots that Hector did, for example, for the latent heat flux gradients and the relative vorticity, it seems that there is a correlation between the filaments of the relative vorticity and the latent heat flux gradients, or the SST gradients. But we have to better understand that, I mean, this is just what we observed, We have to understand that, to quantify that, whether that is true or not. And but so far, what is true is that there is no, the ocean current divergence is too weak to explain the wind stress divergence. And Lionel Renaud found something like that, as I said, in his last JGR paper. So in short, there are still some work to do on that.
Thank you very much, Patrice.
So Megan has her hand up and she has a question in the chat. So Megan, why don't you go ahead?
Yeah, it's the same question. I'm wondering, can you elaborate more on the tropics versus the extratropics and how that might affect or not affect your results here, and particularly the figure that you showed where you were saying that there's a kind of different processes that happen on different, for higher winds or lower winds. And you were saying that in the low winds, that the Lindzen-Negum mechanism, which is the barometric pressure gradient, dominates, but for the high winds, that the mixing dominates. And in the tropics, particularly in the eastern edge of the cold tongue in the east, the cold tongue region, the SST front there, that was originally identified as being stability front, and the mixing as being dominant, even though it would be a low wind regime.
Okay, yes, this is something we have not investigated so far, But from what I understand, maybe Tom can give a better comment than me about that. But the Linson and Nigam parametrization, that is a pressure adjustment, was developed first for the tropics, and to better understand what happens. Now, I'm not aware of any studies who try to relate the wind stress divergence and convergence to the momentum mixing in the tropics. Maybe you are aware about that, but not me actually. So just to answer your question, I think more studies should be done in the tropics about that, and but again, the coupled simulation is wonderful for that.
Okay, but I mean, it was the Wallace et al. Paper and Shelton, really argued very strongly that it was, quasi-stable over the cold tongue, over the very cold SSTs, and then destabilized over the warm water just in the north of the cold tongue. But you're saying that that is not, you don't see that as being a dominant process.
Actually, the argument of the momentum mixing or the secondary circulation argument is that above warm eddies or cold eddies, the size of these eddies is too small for the air masses to adjust to the SST. So usually, and this is what the small and collaborators found, which is a paper I mentioned before, the paper by Justin Small and et al. Published in 2019. In this paper, they try to figure out what happens in the tropics compared with the mid latitudes. And they found that there is a strong correlation between the wind anomalies and the mesoscale eddies. I mean, there is a strong correlation between the wind anomalies and the SST anomalies in the western boundary currents. This does not occur, and which means that the ocean is going to force the atmosphere. Now they found out that in the tropics, the scales of the SST anomalies are large enough for the atmosphere to adjust to the SST field, which means that the correlation, there is a correlation between, there is not a correlation between the wind anomalies and the SST field. There is a correlation between the wind anomalies and the tendency of the SST field, which is different, which means that in the tropics, the atmosphere is going to drive the ocean in terms of temperature.
Okay.
Well, thank you. We are at the end of an hour. So I want to thank Patrice again for a really great talk and a super stimulating discussion. This has been fantastic. Larry has noted in the chat that there's a review paper from the CLIBAR working group that may be relevant to some of this. And maybe, Larry, when you and Hyode have a version that you want to share, we can share that around too. And thanks everyone for participating. This has been wonderful today.
Okay, thanks, Sarah.
Thanks again, Patrice.
Thank you very much.